The kinetic energy of the Tesla is equal to 1/2 of mv squared, where in this case here, my Tesla weighs roughly about 2,000 kilogram, actually 1,000 kilogram, and then you multiply that by v squared. Okay, let's just make it 2,000 to make a round number, so it's 1,000 kilogram times the velocity squared. Later on, we're going to work out examples of calculating the energy of a Tesla as it accelerates from 0 to 100 kilometers per hour. Let me emphasize that E equal to 1/2 mv squared, in this case here, is not a definition. Work equal to F times D is a definition. This is a derived relationship, and we're going to derive that equation. Now, how are you going to do that? Now, as we said last time, that W, the work done as I lift the block by a height of D with a force of F, would that be converted into kinetic energy, in this case here, of the block at the end of that fall. Now, the very fact here that F is equal to ma, this is F equal to ma, simply Newton's law that governs the acceleration of a mass acted on by a force of F has an acceleration of a. So if you have F equal to ma, then work is equal to Fd, and therefore is equal to MAD or MAD. Now, as we have done the calculation earlier, that in this case here, if we assume A is constant, then D is equal to 1/2 of AT squared. And therefore, if you make a little bit of rearrangement, it's equal to 1/2 of m of AT squared. And therefore, it's equal to 1/2 of mv squared. So the work that is done, if you are trying to accelerate the Tesla, push it with a force of F equal to ma, and over a certain time, it will achieve a velocity of v, and therefore, the amount of kinetic energy according to the definition of W equal to Fd, and according to the conservation of energy, that all that work done by the force is translated into kinetic energy, and kinetic energy only, that would be equal to 1/2 mv squared. And therefore, the equation E equal to 1/2 of mv squared is derived. Today, we're going to do an exercise on finding how fast the Tesla accelerates. I drive this car every day to work. So we know that the Tesla, let's say including my own weight also, has a mass of 2,000 kilogram. And when I drive the Tesla and I press down the accelerator, the A could be as much as 0.7 g. And just assume that in the process of acceleration, it's a constant acceleration of 0.7 g, and therefore equal to 7 meters per second squared. So the first question we would like to ask is, how long it takes to go 0 to 100 kilometers per hour. So that's 100 kilometers per hour is roughly about 60 miles per hour. Now we know that velocity as a function of time is equal to AT, and is equal to 100 kilometers per hour, and 100 kilometers per hour is equal to 10 to the 5th meter divided by, there are 3,600 seconds in an hour, and therefore it's given by that. So if on this side here, this is 7 meters per second square, and you multiply that by t, has to be equal to this, that gives you a t of slightly less than 4 seconds. So it takes about 4 seconds for my Tesla to accelerate from 0 to 100 kilometers per hour, and that's a pretty fast car. Now the second question we're going to ask is that during that 4 seconds, the power is supplied by my battery pack, and how much energy is taken out of the battery, and assuming that all of that is converted into the kinetic energy of the Tesla. So what you have here is that the energy is equal to 1/2 of mv squared, where v is the velocity. And so what you have is 1/2 times 2,000 kilogram. And the velocity is basically at 28 meter per second, the whole thing squared. So if you do that calculation, you ended up to have a number which is 7.84 times 10 to the 5th joule. And that's roughly equal to about 10, roughly equal to 1 megajoule. That's plenty of power, or actually plenty of energy that you have to take out from the battery and take it into convert that into the kinetic energy of the Tesla. The third question I'm going to ask is how much power it takes really to move the car over time. Now that part I think need a little bit more explanation. Now we know that power is equal to the rate of change of work over time. And the unit for power is basically watt. Work is joule. Joule per second is a unit of watt. So if you look at that, and we know that work is equal to mat, or m times a times the distance moved. Now given that a is a constant, which I assume in reality a is not a constant, but what you have is ma times the partial derivative of the distance over time, and that's equal to ma times the velocity. So the power, if you look at the power that the car takes out from the battery to move it, is proportional to the acceleration, and also at the same time is proportional to velocity. Which means that at the beginning, since my car starts from a totally stopped position, the velocity is equal to 0. So if you plot the power that is taken out over time, and since velocity is equal to a times t, so it's ma squared t. So what you have is a power curve as a function of time has a slope of ma squared times t. Now, which means that if I accelerate the car at a constant acceleration rate, eventually the power will go to infinity. That's probably not true. I know for a fact that the maximum power that can be taken out from my Tesla is 215 kilowatt. And therefore, this curve had to saturate at a certain point. And in that regard, the actual curve is more like this. The power taken out from the battery start with a 0, and it will saturate at a particular power rate, and then the velocity would not continue to increase at a linear rate, but rather it increased in a much slower rate than a linear increase in velocity.